So this is the problem that we worked in class on Tuesday. This is the lead tin phase diagram. And what I asked you to look at was to look at 20 weight percent tin and to tell me the phase fraction, phase composition, and the approximate microstructure for T equals 400 degrees Fahrenheit and T equals 250 degrees Fahrenheit. So working with this, we're basically going to figure out where we are on the map. And this is our composition in weight percent tin. It's worth noting that in this diagram, we have the weight percent tin on the bottom and we have the atomic percent tin on the top. And these are actually fairly significantly different. And looks a little bit non-linear. Typically we pick the bottom scale to have linear spacing and the top to have non-linear, and the non-linearity becomes apparent because lead is heavier than tin. So as we change the atomic percent, that has a large change in the weight percent. Both weight percent and atomic percent are useful depending on what you're working with. And I chose to use weight percent because that was on the bottom of our scale. So let's draw in 20. So I've got a postcard here that I'm going to use as my ruler. And so 20 weight percent, that corresponds to 30 atomic percent. And next, let's mark 400 degrees Fahrenheit. And again, we have two temperature scales. We've got Fahrenheit on the right and Celsius on the right. Or sorry, the left. So we're in the alpha plus liquid two-phase region. So I'm going to draw this horizontal line. In that region. And then I'm going to draw verticals where our horizontal tie line touches the boundaries. Okay. So this is this is 20. That point is around maybe 18. And that point is around maybe 56 or so. So at T equals 400 degrees Fahrenheit, the composition of the alpha is where the horizontal tie line intersects the boundary between alpha plus liquid and alpha. So alpha has a composition of 18 weight percent tin. If instead you wanted to talk about atomic percent, you can just read that off as well. That's equivalent to around 26, 27 atomic percent tin. And then the liquid has composition of 56 weight percent tin which looks like around maybe what is that? 68 or so atomic percent tin. Okay, so we've got the composition. Now let's get the phase fraction. The phase fraction of alpha is going to be, so the alpha intersects right there, so we go and take the opposite side. So we take 56 minus 20, and we divide that by 56 minus 18, which is 36 divided by 38, which is 0.947. So that's the fraction of alpha, and then the fraction of liquid. That is just 1 minus the fraction of alpha, which is 0.053. So that gives us the phase fraction and the composition. Now let's look at 250 degrees Fahrenheit. So that's going to put us in the two-phase alpha plus beta region. So we're going to draw a horizontal tie line that goes from one edge of the boundary over to the other, and then drop vertical lines. So at T equals 250 degrees Fahrenheit, we're basically looking at, what's that, around 7, and that is around, 98 or so. So the composition of the alpha is where the tie line touches the boundary with alpha. So that puts us at 7 weight percent tin. The beta phase has composition about 98 weight percent tin. If you want the atomic percentages, you can read them off the top. The phase fraction of alpha, so that's alpha over here. So we take this portion of the tie line and divide it by the total length. So we get 98 minus 20 divided by 98 minus 7, which is 78 divided by 91, which is 0.857. So about 86% of our system is alpha, and the beta is 1 minus F alpha is equal to 0.143. So about 14% beta. And now the question is, what do the microstructures look like approximately, assuming that we have, well-behaved solidification. So up here, it's all liquid. we drop into the alpha plus liquid range. And I'm going to use, let's make our alpha phase orange. So I'm going to wind up with that, and it looks like I've got about 95% alpha. So I'm going to draw. So these are going to be our alpha, and then the white parts in between them, there are liquid. Then if we drop further into the alpha plus beta, well, what do we have? Let's see. Just prior to crossing from the alpha plus liquid into the alpha plus beta, it looks like, roughly, still about 95, 96% is going to be alpha, and 4 or 5% is liquid. So we're still going to have that majority of alpha. And I'm gonna pick my magenta to be beta. Now in the regions which used to be liquid, when it drops from the alpha plus liquid into the alpha plus beta, that liquid transforms, and it transforms into the eutectic microstructure, which makes it a combination of alpha and beta, and they're going to have this kind of stacked lathe pattern. So again, this is the orange is alpha, and we've got alpha there, and we also have alpha in between the lathe, and then we have our magenta color, which is beta. And of those, 85% of our microstructure is alpha, and 14% or 14.3% is beta. So this is how to solve problems. When you take the exam this next, I guess it's going to be in a couple weeks from now, this is definitely on the exam, and it's going to be a major component. So you need to know how to read phase diagrams quantitatively, and how to have a good estimate of what these microstructures are going to look like.